Let's have a look at a couple examples from section 4.9. This section covers the topic of antiderivatives. This first one is a fairly straightforward example where we're looking for the family of antiderivatives of a polynomial. Now, here we're using this notation for an indefinite integral. And integration is something we'll get into in chapter 5. At this point, what I would just say about this notation is just to keep in mind what it means. It's asking us to find this set of antiderivatives, okay? And it's, again, it'll tie in with a variety of things we'll discuss in chapter 5. Here, we're using the power rule for antiderivatives, okay, which is a little different but related to the power rule for derivatives. We're also using the sum rule or difference rule because we've got a difference of two terms here. Okay, so in a lot of ways, I mean, you'll see as you go through examples of this, there are certainly connections between derivatives and antiderivatives in terms of their rules. And that's certainly true here. Okay, so when we apply this power rule for antiderivatives, the exponent increases by 1. We divide by that new exponent. Same thing here. Okay, difference rule just means we can do this term by term. But when we get our family of antiderivatives, we always want to remember to write that plus c at the end. Because any constant there, regardless of what value we put in for that constant, we will get an antiderivative for this original function here. And so we want all of those antiderivatives, so that's why we write this arbitrary constant at the end, plus c. So that's an important part of the answer. Here I just simplified the fractions. The test to make sure we get the right answer is if you take the derivative of this polynomial that I have boxed here, it'll get you back to 3x to the 5th minus 5x to the 9th. So that's how you can check whether you have the right set of antiderivatives. Okay, 77 involves the same concepts, but it's asked in a fairly different way. It says, given the velocity function v of t equals 6t squared plus 4t minus 10, find the position function with the initial position s of 0 equals 0. This kind of problem, whether we're talking about velocity or some other function, this kind of problem is called an initial value problem. It's a problem where we're not looking for all of the antiderivatives of a particular function. We're looking for a particular antiderivative based on some initial value. Okay, in this case, s of 0 equals 0. So we know this relationship between position and velocity, that velocity is the derivative of position. So position is going to be an antiderivative of velocity. So we are evaluating this indefinite integral like we did in 23. We do get that arbitrary plus c at the end, but the initial value is going to tell us what the value of c should be. Okay, so here we substitute in, we've got this s of 0 equals 0, so we substitute in 0 for t. This is 0. And we get 0 equals c. So our answer is s of t is 2t cubed plus 2t squared minus 10t. And again, we can check our answer by taking the derivative. We should get back to our velocity. And we also want to check that it meets this initial value, which it does. That's a couple examples from section 4.9. I hope you found this video helpful, and I will see you in the next video.